Alright, this is the final example that I'm going to do for your final, and it's showing the singularities of a matrix, and this is going to be an RRR matrix, a robot. So and I'm going to say that it's got an offset of 1 on each of the joints, a pi over 2 twist for the first two, and 0. And I'm just going to put one offset here, and say this is theta 1, theta 2, and theta 3. These are all my variables. For this one, the Jacobian is ugly. So J11 is equal to negative 1 plus C2, 1 plus C3, that's S1 plus C1, that's 1 plus S3. Negative 2 C1, that's a cosine of Q of 3 over 2 squared S2. Our final entry here is C3, S1 minus C1, C2, S3. Next row we've got C1, that's 1 plus C2, 1 plus C3, plus S1, 1 plus S3, minus 2, cosine of theta 3 over 2 squared S1, S2, minus C1, C3, minus C2, S2, S3. 0, C2, 1 plus C3, S2, S3. This one is ugly. I don't want to give you one like this on the exam. It's not a good use of your time. But if you take the determinant of J11, then you get this particularly enlightening expression. You get cosine of theta 3 over 2 squared times 2 C2 C3 minus 2 1 plus C2 S3. And you think, well, it says something about here that our cosine cannot be equal to, so you don't want theta 3, you don't want it to be equal to pi or 3 pi or negative 3 pi. This is divided by 2, not all that common. And then we've got this weird relationship between the second and the third joints. And so this one is hard to picture. And so what I've done instead is I've made a little model. So if you look at this, we've got our first axis is a rotation joint around the base angle. And it has both a radial offset and a link twist to this next joint. So this next joint, see how it is 90 degrees the first, so we can rotate this around. So together we've got a rotation around the base length and then a rotation around the second length. So we can move this around quite a bit. And but the interesting thing about this second link is it's got, its Z1 axis has an alpha twist. It's also got a D offset and a radial offset. And so our second base is right here that rotates around its new Z-axis here, rotating a revolute arm that's way out here. I don't know why you'd ever make this robot, but you think about it, it's got some degrees of freedom. We can move the hand up and down, back and forth, and then rotate around. And so the first thing to look at is, when theta 3 equals pi, well, that happens when this e-axis is pointed back along the first axis. And the reason why it's a singularity is because now this axis is directly around the origin. And so you've lost a degree of freedom in there, because you can move forward and backwards along this axis, and rotating around here gives you the same movement. See, watch. So rotation around this axis is the same as rotating around this axis. The derivatives are the same, so we've lost a degree of freedom. Now, what does this mess mean? Well, this mess is only related to the first 2 degrees of freedom. And what I believe, and I've plotted it out in Mathematica, and it's this beautiful wavy level set. But what I believe is that somehow you're exploring this surface of a sphere, where again we lose 2 degrees of freedom. So let's see if I can show that. So again, it's only related to these first 2 degrees of freedom. There's certain ways that you can get them to overlap, in which you lose some of your So here is an example where we can move up and down. The jury's out on this one. I'm not going to assign you a problem like this, but you can see that even for a very simple DH parameters, you can get some configurations that look, some singularities that look quite interesting. All right, happy studying. So here are these two terms in the Jacobian, and if they're set to 0, it causes a singularity. The first is the cosine Q3 divided by 2, and the second is this interesting one-dimensional manifold, these lines here. And if the robot is in these configurations, then it loses a degree of freedom.